Our next presentation is a tag team, and most of you know Dr. Steve Morgan from the University of South Carolina. He's a professor in the Department of Chemistry and Biochemistry, and one of his co-workers on this project is Ed Bartick, and Ed is the director of the Forensic Science Program at Suffolk University. And I think Ed is going to lead off.
Yeah, we're not going to hold hands while we do this.
As you can see, also on this project, we have John Goodpaster from IUPUI. The first part of this talk that I'm going to go into is going to be the philosophical part. Also, I'd like to thank the NIJ for sponsoring us in this grant. As we all know, we've had a number of issues that have been brought to our attention in the last few years, particularly in the Daubert hearing, or the Daubert case in '93, brought up the question of reliability, the potential error rate, and so forth and so on. And just recently in 2009, the advent of the announcement of the NAS report. And basically what they're asking in the NAS report is, are saying that we don't have enough of a statistical basis in most of the forensic disciplines except for DNA. So we wanted to take a look at this and what we could do. Now, this is an example of a case that I worked on a number of years ago with Terry Rudolph when I was with the FBI and married Caraba. And just to give you an idea, just to show you, in certain instances, when we're dealing with class evidence, we don't necessarily need statistics. There was a situation where a man came to the captain of the ship, a cruise ship off the coast of California, 2 in the morning, and said, "Sir, my wife just blew overboard." He was a little bit disheveled looking, and the captain looked at his wind speed indicator. It was 2 knots. So he got a little bit suspicious, and they had an investigation. He was thrown in the brig and so forth. 2 hours later, the woman's body was recovered, floating in the water. The Coast Guard had recovered it. And upon examination of her pants, there was some speckled material on there, a dark rubbery-like material there that was also on his pants. And when they examined the track, they were at the location where she went overboard. It was near a running track, and they had apparently been out running. And when we examine this with using infrared microscopy, we look at those specks under the eye, and we obtain comparable spectra of all 3: the track, his pants, her pants, and we actually ran a standard of calcium carbonate in there. Now, this calcite. The calcite is often used as a filler in rubbers, and that's mostly what you could see. There's a little bit of the organic composition in there as well. This combined with the fact that some tests were done on how easily that these materials would get embedded into their pants like that, and this test showed that it was required to rub the pants very rigorously with this track material so that they would have to have been dragged or so forth, and there must have been some kind of fight. Anyway, the person was convicted based on this evidence, and there were no statistics involved or whatever. It was clearly shown that in this situation that the evidence was very damaging. I've got shown here a situation in the Kennedy assassination where a tuft of fiber was found on the gun butt that had been found with Lee Harvey Oswald's prints on it. These fibers that were found on there were examined by the FBI, and fiber examiner Paul Stombaugh testified here that there's no doubt in my mind that these fibers have come from this shirt. However, his next statement was that there is no way, however, to eliminate the possibility that the fibers come from some other identical shirt. And this is the crux of the problem that we deal with class evidence. And so we wanted to take a look at this. Now, at the last trace evidence symposium, we had a Daubert hearing, moot court, if you will. And Amy Michaud got up there on a fiber hearing, and what she was able to say based on the evidence that she found with the fibers, and this is like 50 years later, the data obtained from the question evidence specimen was consistent with the known specimen. Again, we still haven't advanced to being able to put more statistical information based on the meaningfulness or the significance of this. Now, DNA has, of course, come its way, and the fact that it's able to make reliable and accurate statistical inferences from the profiling, it's beginning to force the issue that we need to do something in this regard. And there's been many talks during this conference that have talked about different really sophisticated ways of doing the analyses in this, and this was the most current one was very, very impressive. However, with DNA, and if we look at the 13 loci that are used in the CODIS, and we look at the percentages based on the population and studies that have been done on that, and which are very low individually, if we multiply these, we can get up into the quadrillions, a 1 in quadrillion amounts, which is very significant evidence. Now, another example in the of trace evidence was in the Wayne Williams case, and I'm not going to go into the slide that's overly detailed, but I want to look at two fibers that types of fibers that were looked at on two of the victims. And one, of course, was the bedroom carpet fiber, which was a very unusual carpet fiber, and one from the station wagon. And these actually, in this instance, Hal had actually calculated out or he had a team that worked on this that determined the sales versus the square yardage of carpets there, and actually came out with a probability of 1 in about 8,000 for the carpet fibers and 1 in 4,000 for the automobile one, the station wagon one. Now, these were not just shown at court, and the product rule wasn't used, but if you calculate the product rule, considering that these are two totally independent variables, it comes out to be 1 in 30 million. So in this particular case, this was a very high-profile case, and it was a great deal of effort work went into this. However, we couldn't potentially do this in every case. I'd like to show you a quote, a very profound quote that was back in 1897 by Oliver Wendell Holmes, a good old Massachusetts guy. For the rational study of the law, the black-letter man may be the man of the present, but the man of the future is the man of statistics and a master of economics. And that was extremely profound, and we haven't really seen the reality of that except in DNA analysis of that. Now, one of the ways to approach this, I feel, is based on a quote that I made a few years back in 1988 when I was interviewed for an article in a magazine and indicating that digital libraries containing analytical instrument data plus chemical, physical, manufacturing information materials frequently found at crime scenes are a means to provide a statistical basis of materials. And I think once we've got that information, we can look at the different data of the different features and start building a statistical basis and potentially eventually apply a product rule type of thing. But we're not anywhere near that yet. We've got a lot of data to collect, and the person who's going to get into, whoops, I forgot about this. These are some databases that have been done over a period of time, the last 20 years or so, and by different people, some in my lab and some in other labs. Some are just identify materials. Others start getting into more detailed about this, like the automotive paint PDQ database, which has come into an international database, and that's based on a characterization of the materials in there. And in the process, we've had a collaboration with the University of South Carolina when I was with the FBI, and a database was beginning to be developed by total characterization as well. And Steve is going to get into exactly how we plan on delving into this kind of database.
Thank you, Ed. So our current NIJ grant has the following research objectives. And perhaps we bit off more than we can chew. They only gave us a year to do it, which is interesting. But we're trying to do a lot. One of the major things we're trying to do is use our database advantage, the fact that we do have a good collection of fibers, and use those fibers to promote an interlaboratory study. We actually have 6 collaborating laboratories, the 3 academic labs, the principals of this talk, and then 3 forensic labs in each of those cities. In Columbia, South Carolina, for example, the State Law Enforcement Division lab is collaborating with me. We're going to investigate, we're going to do some interlaboratory studies that compare the judgment of forensic trace examiners on fiber identification, fiber matching, to some of the statistical approaches that are available. We're also going to evaluate interlaboratory variability. How much variability do we get between decisions made in different labs with regard to different measurements? And what sort of error rate we get on our misclassifications and misidentifications. All of this throughout, we're going to try to document what we feel are good practices and write protocols that we think are working well for us. And then eventually, too, throughout the whole process, develop a prototype forensic database that will integrate electronic signatures for documentation on the type of data stored, the type of material stored, data validity checking of all that, and relational database searching. So the first step in the database and building a database is simply understanding the parent population from which you're trying to create a database. And there's a host of questions you should consider. How is the item made? Who are the major distributors? Does the item carry any markings that are traceable to a retailer or distributor? Is the item regulated in any way? Has the formulation changed with time? How common is it? In what regions of the world or country is the item more common? And what is the typical life cycle of the item and how long it's used before disposal? And then along with that, how does it degrade with time, okay? All these are important questions. So in studying class evidence, the first step is to acquire a representative collection. And John Goodpaster actually wrote the original version of some of these rules for guidance for our project, and they're really quite good. Acquire multiple items of the same type. Why? You get the diversity of the variation in those types. Acquire multiple items from the major manufacturers and distributors. Ideally, the makeup of your collection should reflect the market share and the availability of those items. Try to make it geographically diverse, at least over the area that you're interested in covering. Your sample should cover that same area. And how many is enough? You know, this question is a question that statisticians always hate. How many is enough? You know the answer that statisticians give all the time? More, right? More. So that's what we're trying to do, get more. Originally in 2003, 2004, we started a database of fibers at the University of South Carolina. Initially, it grew to about 300 fibers, and within 2 years, we had about 500 to 600 fibers. In the last year, we've grown it to 914 fibers, and this particular collection is of the 4 most common fiber types: acrylic, cotton, nylon, and polyester. And not only do we have fabrics, okay, that are dyed with these dyes, but we have the formulations of the dyes. We know the dyes that were dyed on each fabric, and we have samples of the dyes. And so this is just a wonderful database to play, analytical chemistry games with. Since then, and the data is all organized in a Microsoft Access database. The samples are actually stored in plastic protector pockets that I actually acquired from a rare coin dealer who sells this acid-free protective material. And they're actually inside these pockets and then placed inside the like 35 millimeter slide pages of the pages. And that provides a secure, long time storage. And we also store them in the dark, of course, to avoid fading of these fibers. Now, it turns out just recently I delivered a copy of the 914 sample collection with the database to my collaborators. And taking the samples out to SLED, they were just overjoyed because they didn't have an organized collection. And they said, "Oh, we have a collection." I said, "Well, where is it? Show me." And so we went to a closet in the back of one of the labs. It was dark in there, and we were fumbling around. And I discovered 500 fiber samples there that were totally disorganized. And so I put three undergraduates to work cataloging them and entering them into our database. And so within 2 weeks, our fiber collection expanded to 1,400 odd fibers. And then it turns out I turned around and looked over in the corner, and in the corner there were some 70 large panels with swatches of carpet fiber that had been obtained just a few years ago from, I think it was Lowe's hardware store and Home Depot, or some of the local home supply stores. And each panel is of a different color, the same dye on the whole panel, but the 20-odd smaller panels on each panel of cardboard represent lighter and lighter dyeings. And so this is also a very interesting collection that we're going to add. There's 1,400 carpet samples there, and we're going to be adding those and cataloging those in our collection too. Now, Ed mentioned statistics is the way of the future. I think economics better be soon, the way the world is going. But this is an old data set, and I've talked about it extensively, including on a poster at the 2007 meeting. This is a data set that I published in this book chapter with Ed that Ed Blackledge wrote. And it turns out that this data set has spectra from 7 fibers, and they're color-coded with different colors here. There are 10 replicate spectra of each fiber. And I thought I'd just use this simple example. I had some more complicated data sets from our current work, but this is an old trusted one. It turns out that if you gaze your eye across the 3D portrayal of these spectra, there are some fibers here that are similar, particularly in the middle. The light turquoise fiber and the purple one next to it have very similar spectra. And so if we look at those the group 4 and 5 from this group of 7 spectra, one thing you might want to do is simply make a stack plot of the replicate spectra from each of those groups. And what I've been working on the last few years is software that does, sure enough, some of the heavy lifting, stuff like principal component analysis and linear discriminant analysis. But it also has in this software right now about 40 different ways you can plot your data. And this is one of the ways, just a simple stack plot. And that's a beautiful way to look at the data. And this is what we would like to be able to do right on top of our instruments, but I don't think the instrument manufacturers have quite caught up to exploratory data analysis on the fly right after you take spectra. But the nice thing is, looking at this, I don't think any fiber examiner in the room would say that these 2 fibers are different, because the red and the blue lines overlap with one another. Now, another simple display I have in the program is simply the ability to plot all of these spectra belonging to one group against all spectra belonging to another group. If these 2 groups of spectra are exactly equivalent, this would be a perfect straight line. If it differs from a straight line, then perhaps they're not so exactly equivalent. But here's that plot. And so there's little X's on this plot that is each one of the pairs of data for comparing all members of one group to all members of the other group. And it turns out that when you calculate the R squared, or the R, this is the correlation coefficient, this is the square of that, the coefficient of determination. The correlation coefficient is often published in or given by statistical matching programs, statistical library searching programs, and the 0.9981 is a pretty good match, okay? I'm a little reluctant to say that you should look at one number to categorize the relationship between 2 multivariate patterns, right? But nevertheless, this is an easy display to create, and it gives us some confidence in our initial presumption that these 2 fibers can't be distinguished. Let's look at 2 fibers that are, in fact, completely different. And I didn't plan this, but this was actually the second pair of fibers I looked at when I had this program working, and I was just amazed to see that for 2 fibers that were different, it came up with a question mark. Isn't that beautiful? If software were only so intelligent, right? But clearly, the correlation coefficient for these 2 fibers is only 0.59, okay, a big difference from the 2 fibers that were really consistent with one another on the previous slide. And the experienced eye recognizes large differences in this region. And by that, I mean large differences between the 2 groups relative to the variability between the groups, right? That's what we look for. That's what you should look for. What do you need to be able to do this? You need replicate spectra. And if possible, you need a lot. Now, what do the SWGBAC guidelines say? They say take more than 1, right? In fact, they say maybe take 5 to 10, depending on the type of fiber. I think 10 is really a minimum to do a good job of comparing fiber spectra. But anyway, it's interesting that this pattern is so cranky. It's clearly not a good match, okay? Now, the other question, though, this is, I picked two things that were really obvious, one that matched and a pair of fibers that didn't. How do you decide the more close cases? Well, let me give you a hint of this. The program also generates distributions of, on the left in each case, all of the samples, all of the spectra that do not belong to the same group and the correlation coefficients. With the group 1 and 7 comparison, there are 100 such correlation coefficients possible to generate. And the distribution of those looks right here. The maximum R value that you get from samples that do not agree with one another is 0.5139. I'm sorry, the maximum is 0.6781. And on the other hand, this little distribution here is the distribution of all the correlation coefficients between spectra that are in the same group, that belong, that really should be equivalent, right? And the minimum R for that side of the distribution is 0.975. Clearly, these 2 points do not overlap. There's a gap here, okay? And of course, with closer differences, this gap begins to disappear. But this does give you some statistical basis for saying that, yes, this is a difference, and it is statistically significant. There are some hypothesis tests that you can conduct as a consequence of this. Anyway, this is the groups 4 and 5 that I did first that are very similar spectra. And it turns out the two distributions for the correlation coefficient between spectra that do belong to the same group and don't belong to the same group, they overlap with one another. Okay? And so that's statistical justification for saying, indeed, that those two fibers cannot be discriminated. Now, I have a lot of other bells and whistles, and this is one I've had in there for a long time, but more recently I've implemented this as a way for the investigator to focus their interest on the regions that are of importance. Remember a little while ago I was saying, look at the region where the differences between the spectral profiles was great, and the variability was much, much smaller than that for each group, right? Well, that's exactly what this plot does. This is the plot for the two dissimilar fibers. And what I'm doing here is I'm doing a one-sample t-test. I'm sorry, a two-sample t-test, for a two-sample t-test for the significance of the difference between the two group means for 10 spectra from one group versus 10 spectra from the other group. But I'm doing it at a single wavelength 1,575 times, because I have 1,575 digitized points across there. Now, I don't think I see any of the statisticians that were in the workshop on statistics on Monday here, but statisticians begin to shudder when you start doing so many tests like this. And they say you're losing control of your alpha, because what happens is that your error rate is magnified by doing multiple tests, and the error rates effectively multiply. And although you may be doing each test at the 95% level of confidence, your overall error rate of making a mistake somewhere becomes very, very significant. And the green line actually is the students, the critical value of students t that you could look up in the table for one of those tests. And the red line represents what's called a Bonferroni correction value that sort of controls for that loss of control of your level of significance. And so an investigator could, for example, say the regions that are above the red line are regions that are significantly different between the two groups, and thus are regions where I want to focus my attention. If I wanted to do further multivariate analysis like PCA or LDA, my program even allows you to say, at this point, I want to do feature extraction, and it will delete those regions that don't meet that threshold, okay? Just as an aside, this is becoming very important on a project we're doing trying to discriminate mass spectra taken on MALDI-TOF of breast cancer cells and normal cells, where the mass axis goes out to 360,000 mass units. And the number of features is actually in the 700,000 range. And so we need to do this sort of feature extraction to simply reduce the number of features to a manageable level. Anyway, here's the same test done on the two groups that are indistinguishable, the two fibers that are virtually indistinguishable. I want you to notice two things. One, the axis labels are not very high differences here for the calculated t statistics, whereas this goes up all the way to 60, okay? So that clearly shows you that this is an example of two fibers that can be discriminated. This is a sample of two fibers that probably cannot be discriminated, even though certain parts of the spectrum, and in fact, these parts of the spectrum are some of the same parts, but because of the low t statistic, I would not put much reliability in any classification on the basis of trying to discriminate those two groups, simply because this is weak evidence compared to the evidence on the left. Okay, so there's other ways you can look at the data, and we've talked about linear discriminant analysis and principal component analysis. I'm not going, this has been discussed earlier in this symposium this afternoon. Basically, linear discriminant analysis, for example, gives you a map of the similarity of the samples. And the two groups that cannot be distinguished in this particular data set are the groups 4 and 5 over here, and the ones that I was comparing before were group 1 and 7, which are clearly different from one another on this map. Now, in fact, because I know what the dyes are, I understand the chemical reason for these differences as well. You wouldn't know that in a particular case, but it turns out these two fibers were dyed, well, on the same process, but weeks apart with perhaps a different dye badge. And they're very similar, but they are overlapping quite a bit, okay? So that's the reason. I think it was Ronald Reagan who made this phrase famous, but it's actually an old Russian proverb, and it's interesting that he threw it back at the Russians when he did. But there are all sorts of validation procedures you should be doing when you use statistics. We classify samples by measuring to the nearest group, and we do cross-validation by leaving one sample out, fitting the model without that sample, putting it back in, and predicting membership, okay? So there's a lot of work we're doing. And I thought I'd finish with just this one plot. I just picked this one because it's a group of 17 brown acrylic fibers. And many of these are of, some of them are of light shades. And this is the linear discriminant analysis plot. So this is the best discrimination you can see in 3 dimensions with these fibers. And it's interesting because you see groups of fibers over here on the far left that aren't very distinct from one another. In the middle lower part of the plot, you see fibers that are also very close together. In the upper right, you see some that are close together and one that's way out in left field. This is one of the samples, one of the sets of samples probably that we're going to use in our interlaboratory study because it has a nice mix of things that are readily discriminated and things that are going to be much more difficult to discriminate. And it's going to be very interesting to see how fiber examinations using traditional methods and eyeballing it compares to the statistical approach. With a model on all this data, it turns out we can discriminate 86.47% of these spectra from one another. It turns out 10% of those misclassifications are due to fibers having the identical dyes. And that's the other thing that's in here. There are some fibers that have identical dyes, so that'll be a nice test of performance. So anyway, I'd like to thank the host of undergraduates at the University of South Carolina that have worked on our database and worked on UV visible microspectrophotometry over the years. The current students, Molly Burnip, Audrey Fennell, Scott Hoy, Nick Riley, and Patricia Shelley in particular have worked very hard on growing our database. There's a reference to Cheryl from John Goodpaster's lab, who talked earlier, who's going to be working on this in the next year, and a couple of undergraduates from Dr. Bartick's lab that have been working on it. So thank you very much for your attention. I'll end here.